Okay, welcome to CULINOLOGY 101, the last chapter. Okay, last chapter we're going to talk about food emulsion system. Okay, so for the learning objective, okay, at the end of the chapter you'll be able to understand how the emulsions are formed, how it can be stabilized, and what are the destabilization mechanisms of food emulsions. Yeah. Okay, let's look at the first thing first. All right. What is the characteristic of emulsions? When we talk about emulsions, it usually consists of two immiscible liquids. Okay, two immiscible means that they do not mix with each other. Okay, usually in this case is oil and water. Yeah, oil and water is basically the two main components of food emulsions. What happens is that with these two emulsions, one of the liquid will disperse as a small spherical droplets in the other. Okay, so it will definitely be a spherical. Yeah, okay, spherical means round shape. Okay, the reason why is it will round shape is to minimize the surface area. Okay, to have the minimal surface area, the contact between the two areas. Yeah, okay. So when the two immiscible liquids, as you have learned from organic chemistry, oil and water, oil is non-polar, water is polar. Yeah. So these two do not like each other. Okay. So if we are able to form an emulsions, the two of the liquids, they will disperse. Okay, as a small spherical droplets. Okay, as I mentioned, why it has to be in the spherical droplet is to minimize the contact between the two liquids. Okay, to minimize the two liquids. So in the sphere, okay, it can be either water or oil. If the spherical is oil, then the surrounding media, okay, all this area here will be water. If it's water, then the surrounding will be oil. Okay, so basically it will be either one. Yeah, okay. So if it's in the emulsions, basically the next slide, if you look at this, we actually have two different systems here. We have oil in water emulsions and water in oil emulsions. Okay, oil in water emulsions, or you can use this abbreviation O/W. Yeah, oil in water. Yeah, emulsions basically consists of oil droplets dispersed in an aqueous phase. Okay, so it's basically in this case the aqueous phase, right, is water. Yeah, it's water based. So basically this oil and water emulsion is one of those that is very common in food products. Okay, for example like milk, cream, dressing, mayonnaise, beverage, soups, sauces, all these are considered as oil and water emulsions. Okay, if you look at the system, right, basically they have a lot of small oil droplets. Okay, the droplets can be different sizes. Okay, so all these are oil droplets, and the dispersing medium, right, is basically water. Yeah, so all these oil droplets are suspended in the water. Okay, that's why it's called oil in water emulsions. Whereas the other one is called the water in oil emulsions. Basically, it consists of water droplets. Okay, all these are all water droplets suspended in oil. Okay, so there are two different types here: oil in water and water in oil emulsions. So this one is basically the emulsions, the final product emulsions. Before I talk about the emulsion producing process, you can see over here the emulsion is white in color. Okay, why is it white in color? The reason why, if you look at water is transparent. Okay, oil is also translucent. Okay, then the emulsion form is white color. Why is it white color? Is because the droplets. Okay, so if you look at the emulsions, imagine, yeah, all these are very small, but I just enlarge it so you can see all these are very small. Yeah, in the naked eye you cannot see. Yeah, so what happened, right, is that when the light go through, okay, it will bounce off. Okay, because of oil droplet, it will bounce off. Okay, Because of this bounce off, it causes the light, what we call light scattering. Okay, so the light will be scattered around. So the reason why it's scattered around is because the oil droplet, okay, reflect, okay, the lights here. Okay, because of this scattering, that's why it's white in color, because it cannot go directly into your eyes. If you're looking at those that transparent, so like water, there's no oil, so the light will go directly to your eyes. So imagine here is your eyes here. Okay, so this is your eyes. So the light directly go to your eyes, that's why it's look at transparent. But why this is the white color is because it bounce off, so it scatter around, so your eyes cannot directly have the light. Yeah, that's why it looks white color. Okay. So in order to produce emulsions, you will need to input of energy. Okay, you need to input of energy. Yeah. Usually this process of input of energy is called homogenizations. Okay, homogenizations. Basically, the mechanical device used for homogenization process includes like high-speed blender, high-pressure valve homogenizer, or colloidal mill. Yeah. So all these different type of the tools, you can use it to homogenize between the oil and water. If you're looking at all these different type of the devices, there's a difference in terms of the energy input. Yeah, what happens is that the higher the energy input, usually will lead to smaller droplet size. You can see from here, the droplet size, the oil droplet size or water droplet size, right, can range from 0.1 micrometer. Yeah, micrometer is very, very small. Yeah, 0.1 micrometer to 100 micrometer. Usually, if you have input of a lot of energy, okay, then they will go smaller. Okay, the more energy input to the system, then the droplet size produced will be smaller and smaller. Okay, so if you're looking comparing, like for example, the high speed blender, okay, with the high pressure valve homogenizer or colloidal mill, these two, high pressure valve homogenizer and colloidal mill, usually they have higher input of energy compared to high speed blender. So in that case, these high pressure valve homogenizer and colloidal mills will produce a smaller droplet size compared to the high speed blender. Okay. Okay, why is it kept emphasizing on the droplet size is because usually if you produce smaller droplet size, the emulsion is much stable. Yeah, the emulsion is much stable with a smaller droplet size, because the density difference, okay, if you take slower to actually raise to the top, okay, because oil is lighter density, the smaller droplet size, then they will have a smaller, okay, slower in rising up to the top. Okay, that's one thing. And secondly is that they usually they will have much more surface area to actually stabilize them. Yeah. Okay, how you can determine the droplet size is using what we call a particle sizer. Okay, is what we call a particle sizer. Particle sizer. Okay, so particle sizer is a machine that to determine the droplet size in the emulsions here. So the machine is very simple to use. Basically, you just take some of your emulsion and drop into the cone, and then it will go through the system, and using the light, the laser scattering, right, to determine the size of the particle size of the emulsion droplets here. Usually, you can see that there's a distribution here. The smaller the gap of this distribution, okay, means that it's more even. The particle size is very, very even here. So you can see from here, for these emulsions, the droplet size range about like 5 micrometer to about 13 or 20 micrometers, yeah, with the mean size is about 9 point something or 8 point something micrometers, okay. So the smaller the gap is better, okay. The wider the spread usually means that you got a lot of means that you got very small droplet as well as large droplet that is not so unified, okay, and usually is much more difficult to control, yeah. The reason why you got a wide range, right, got a lot of reasons. One, it could be due to the type of emulsifier you use. Okay, sometimes it got to do with the device you use it to homogenize as well. So a lot of factors. Yeah, I won't drill too much in it because you will learn that later on in the food chemistry. Yeah. So what happened after homogenization? Okay, so far what I have mentioned, right, is only oil and water. Okay, so even though you can form what we call emulsions by using just oil and water, because you input a lot of energy, so you actually make into smaller droplets. So even though you can form emulsions through using pure oil and water, but very fast if you separate back into a layer of oil and water, okay, if without what we call an emulsifier. Okay, I'm going to talk about what is emulsifier. Yeah, so you can see from here, there's a oil layer, there's a water layer. Okay, without this emulsifier, so you can homogenize and form this, but very quickly these emulsions, okay, it can be within a few minutes to 10 minutes or so, you will separate back into a layer of oil and water, yeah, if without emulsifier. So you can see from here, like vinaigrette is that's why it's an emulsion without the emulsifier. You actually can form the usually you can form the emulsifier, but very quickly it separates back into the oil layer and the water layer, yeah. So you will need something called the emulsifier. I'm going to talk to you later what is emulsifier, yeah. Usually emulsifier, it contains a distinct end. One end which is polar, another end is non-polar. So it's more like grabbing. It's a molecule that you grab two sides. You grab the polar and the non-polar oil and the polar water together. So in that case, right, they can remain as a emulsions. Yeah, it can remain as an emulsion because you got something holding it. The emulsifier hold both the sides. Yeah. Okay, so basically what I have mentioned is that the emulsion is stabilized using the emulsifiers. So the emulsion itself is basically what we call thermodynamically unstable. Okay, thermodynamically unstable. So without anything, because of its thermodynamically unstable, if you separate into a layer of oil and water. So how you can make it as a kinetically stable emulsions, okay, how you can make it kinetically stable is through using either an emulsifier or texture modifier. Basically, these two substances will act as a barrier, will act as a barrier to actually stop or not stop, actually to slow down the process of changing it back into a oil layer and a water layer. Okay, so the kinetically stable, as I say, will slow down. It can slow down the process to maybe a few days, okay, to weeks, to months or years. Yeah, it really depending on what kind of the emulsifier or texture modifier you use. Okay, let's talk more about these two substances, yeah, emulsifier and the texture modifier. Emulsifier is basically an amphiphilic molecule. Amphiphilic means that it got two extreme ends. Yeah, amphiphilic means that it got two properties. One one side is basically hydrophilic, another side is hydrophobic. Yeah, so this molecule has both a hydrophobic and hydrophilic area, and what we call is amphiphilic molecule. Yeah. Okay. So what happens is that these two ends, they will absorb to the surface of freshly formed droplets, or what we call the interface. Yeah. So you can see from here, this one is oil and water emulsions. Okay. So you can see here, the right side here, oil and water emulsions. So this is the oil droplets. So the emulsifier, you can see, they absorb to this region, what we call a interface. Yeah. Interface. Okay, interface. So they absorb to the interface. The hydrophilic part of the emulsifier will interact with the water. The hydrophobic part will interact with the oil. So they actually form what we call a barrier to actually stop it from separating. Yeah, because if without that, then the oil and water will be incompatible. Okay, because non-polar cannot interact with polar region, the water, so they will separate. Okay, they will say, but because of the emulsifier, then they are more or less better. Okay, they can withstand with each other longer a bit. Okay, until the emulsifier can be destabilized, or the condition can be destabilize the system. Yeah, later we're going to talk about the destabilization mechanism. Yeah, so the emulsifier can be in this case is water in oil emulsion. You can see that the hydrophilic part is now pointing into the water droplets, and the tail is now going to the oil droplets. Yeah, so this one is basically emulsifier. Of course, the emulsifier, if you're looking at the industry, or the manufacturing, there are a lot of different types here. So please choose wisely. Again, more details about emulsifier you will be learning in the food chemistry. Yeah. So another one is called texture modifier. This one is texture modifier are thickening agents. What happens is that you can use this thickening agent or the gelling agent to actually stop the oil from separating from water. Okay, they will stop, basically physically they immobilize it. They cannot separate with each other. Yeah, because of the textural modifier. But you may say that, sir, so this one, why don't we use textural modifier? It will be fantastic for stabilizing emulsions. But what happens is that now your emulsion is going to be very thick. Okay, very thick, and possible it actually affects the mouthfeel. Yeah, so not necessarily the textural modifier will be suitable for your food products. Okay, usually people are still going to the emulsifier, yeah, to give you a fluid emulsions, okay, which is in the liquid form, and it can be pourable as well. Yeah. Okay, so there are these two types here. So I'm going to talk more about emulsifiers. Okay, emulsifier, there are different types of emulsifier as I mentioned before. But basically, if you're looking at the emulsifier, they got even though they got different type of emulsifiers, they can actually categorize, or maybe they can break down to two different types of stabilization mechanisms here. So the emulsifier can stabilize either through what we call electrostatic stabilizations or the steric stabilization, or sometimes they combine these two mechanisms to stabilize the emulsions here. Okay. Again, it really depending on the emulsifier molecules here. What is the structure? Okay, does it contain charge? Is it very long? Okay, is it a bulky one, or so forth here? Let's look at the first, the stabilization mechanisms here, okay, for the emulsifier. For electrostatic interaction is when the emulsifier absorb at the interface, they got one region that is sticking out from the, it can be oil or water droplets, okay, they have charge, okay, when they have charge, so you can see the emulsifier, just say do over here, and this region they have charge, can be positive or negative. Okay, in this case what is showing, right, there's a net positive charge at the outer layer, so a lot of emulsifier over here, and because of the emulsifier, the region up here, there's a net positive charge here. So because of that, there are a lot of net positive charge that is surrounding the droplets. So imagine every droplet there are positive, net positive charge. So when they try to get close together, what happens? Positive to positive, they're going to push them apart. Okay, they push apart. So this kind of emulsifier, again, is depending on the emulsifier. Okay, and these are the emulsifier with charge, yeah, with charge at the region, yeah, at a certain region. If they do not have charge, then they cannot have this kind of stabilization mechanism. Okay. Another one is called what we call steric stabilization. Okay, steric stabilization is when the emulsifier are very large. Usually, if the emulsifier is very large, then they actually can extend all the way out from the emulsion droplets. Okay, when they extend out from the emulsion droplets, this extended region become a physical barrier. So they actually, when the two emulsion, when want to come close, they actually stop each other with the hairy layer. Yeah, with the hairy layer, they actually block each other from going too close to each other. Okay, physical barrier. This one usually are those large emulsifier molecules. The emulsifier molecule usually are large in size that can then only can give this kind of steric stabilization. Yeah. Sometimes the emulsifier contains a large region, okay, as well as maybe this region they can give like net positive or net negative charge. Okay, in this case, then they stabilize through a steric as well as through electrostatic stabilization. Yeah, so it really depending on what kind of emulsifier you are talking about. Okay. So this one is stabilization mechanisms. Yeah. So looking at this, you can see from here, this is the original emulsions that is being stabilized by the either through the electrostatic or steric stabilization. Okay, so this one, it can without any interfere, this kind of emulsion can last probably like from few weeks to months to years, yeah, really depending on what kind of the stabilizations. Yeah. Okay, but what happened, right, is that when this emulsion is subjected to a change in the condition, okay, the emulsion condition has been changed. For examples, it can be due to the emulsifier network at the interface. Okay, the emulsifier may not be strong enough to stabilize for long term. Okay, for example, okay, maybe a very short chain or very weak charge, so it cannot stabilize for long. Sometimes the time factor itself, okay, can make it worse here. As you store longer, they may not be able to stabilize for that long. Okay, so when especially when your formulation has all these conditions like salt condition, pH, or sometimes caused by the microbial growth, all these a change in the environment condition, and when you give enough time, then they can destabilize. Okay, they can destabilize. How is being all these are what we call the destabilization mechanisms. Okay, how it can destabilize? You got a few different ways. The first thing, the first few, one of the way is what we call coalescence. Yeah, coalescence is when the droplets they merge together. So what happens is that the emulsifier can no longer form a barrier. So the emulsion and emulsion, the emulsion droplet and emulsion droplet collide with each other, and then they form from a two smaller droplets into a larger one. Okay. So what happens is that the larger one can actually form okay, collide with the other one to form even the larger droplets, okay. And this condition from smaller droplet to larger droplet is what we call coalescence, okay, coalescence. Another scenario is what we call flocculation, yeah. Flocculations is when the emulsion droplets, they stick with each other, okay. Possible is that it could be have lost the charge, okay. For example, a change in pH or increase in salt content. What happens is that the charge reduce. When the charge reduce, what happens? They cannot repel. What happen? They stick to each other, okay. This is what we call emulsion droplet flocculation, okay. They stick to each other. But the emulsifier is still forming a barrier in this case, so they did not merge together, okay, which means that it did not coalesce, yeah, it didn't lead to coalescence, okay. This is flocculations. As I mentioned, when either it become bigger or the cluster become bigger, the difference in the density is higher. So what happened, right, is that eventually when it's high enough, it's going to float to the top. When it float to the top, this is what we call creaming, okay. This is what we call creaming. So you can see, okay, when you can see that when you looking at the emulsion droplets, yeah, this is a beaker with your emulsions. Then slowly you can see that the thick layer, the white color, right, it start to go up. Yeah, the white color start to go up to the surface. This is what we call creaming. Once it go up, what happen? Down there become either water and oil, okay. So you can see that it become more and more transparent, yeah. It become more and more transparent as the emulsion droplets float to the top, okay. So when it's reached the top, what happened? It became very compact. When it become compact, then it can lead to coalescence to form back into oil and water, okay. Become oil and water. So all these destabilization mechanisms, okay, you can actually use the droplet size or particle sizer, right, to trace it, yeah, to actually track it or monitor it, okay. So you can use the particle size to monitor the droplet stability, okay. For example, from here, okay, original from here, then you can see that it shifted, okay, it shifted. Okay, so this, instead of like a sharp end, this curve shifted over here, which means that now you got very small droplet and very large droplet, yeah. Okay, when it shifted, you know that it become unstable, okay. Yeah, it can be due to the merging coalescence, it can be due to flocculation, okay. You can also use it, the particle size, to understand the effectiveness of homogenization process, as well as knowing whether the emulsifier you use can form a homogeneity or the heterogeneity of the emulsifier that you use to form the emulsions here. If it's homogeneity emulsifier, usually the peak is very narrow. This is very narrow, okay. If it's heterogeneity, usually it can have very small droplet to very large droplet, yeah. The reason is because if you got homogeneity, usually they only have one emulsifier. Homogeneity means you got one emulsifier, and one emulsifier usually it can form a very sort of like a particular droplet size, that's it. But when you got heterogeneity emulsifier, some emulsifier can form smaller droplets, some emulsifier can form large droplets. That's why usually the curve of using heterogeneity, it can vary a bit more, yeah. The curve will be slightly wider a bit. Okay, so I will stop here, okay. So this is all about emulsions. So make sure that you ask questions in Padlet if you got any questions. If you got no question, please indicate no question in the Padlet, yeah. Do attempt the tutorial quiz, okay. It will help you to emphasize some of the keywords that are mentioned in this lecture, okay. Thank you very much.